Hey guys, it's Miss Johnson and I'm here to bring you our first notes video for chapter 11.1. We are splitting this section in the book into 3 different parts, so hang tight. This is the first of 3 videos for this section. We are getting into significance tests, or in other words, hypothesis tests for means in this chapter. That's how things are going to look a little bit different. We have so far done confidence intervals for means. We've also done significance tests and confidence intervals for proportions. So this is kind of the last piece of that 4-part scenario that we had going on. We're going to round it out with significance tests for means in chapter 11. The good news, a lot of it is stuff we've been doing now for nearly a month, for the last 3 chapters. We have to construct our responses as state, plan, do, and conclude. We just need to use the appropriate formula, make sure we're picking the right one, but we're still stating conditions, we're still naming the test, we're still listing the p hat or the x bar. In this case, it's x bar. So all of those things are still the same, which is kind of nice. So here's our conditions for a significance test. We have to make sure that the data comes from a random sample from the population of interest. We also have to talk about the 10% rule when we're sampling without replacement. Remember, that 10% one is the one that you only need if you're sampling, not if you're doing an assigned experiment. And then we also need to address the normal or large sample part. If we're testing the mean, that means we don't know the population mean, which means we can't actually say that the population is normal. It's rare that they will tell you that the population is normal, but as long as your sample size is large enough, then you're good. If your sample size is not large enough, then you need to graph your data. So making a graph of the sample data to assess the normality of the population. When you graph the data, you want to look for the skew or outliers. So all of that is the same as when we were doing confidence intervals for means. If we didn't have a large enough sample size, we would make a dot plot usually of the data and look for outliers or skew. One thing about the AP exam, you may use your calculator to do a lot of that work for you. You may put your data into your stat editor and you may have your calculator graph the data for you. It's not enough to just say that you looked at a graph. You have to actually make a sketch of the graph on your paper when you're taking the AP exam. So just a heads up, make sure you're putting that graph out there so that they know that you have looked at it and they can see the graph that you're referencing. So let's just take a look at this first example. It says, here are the lifetime and hours of 15 deluxe AAA batteries from a company's simple random sample. Check if the conditions for performing a significance test are met. So the first thing, we want to check random, okay? And it says random sample, SRS, of 15 batteries. So that's enough there, check. 10%. Here's where you kind of just have to make an assumption. So we're going to assume that 15 is less than 10% of the number of batteries that are made in that day. So we can assume that 15 is less than 10% of all deluxe AAA batteries this company made that day in a day. If a company opened its warehouse and made only 150 batteries in a day, that would be pretty shocking. Like, we're pretty confident that they are going to make more than 150 batteries in a day. Okay, and then the last one, normal large counts. So for normal large counts, we don't have a large enough sample size. So that's the first thing. 15 is less than 30. So we check a graph. I'm going to make a dot plot. From my dot plot, I need to go, my lowest value looks like it's 17. My highest value looks like it's 51. So I need to go from about 15 to 50, something like that. So this is going to be 15, 20, 25, 30, 35, 40, 45, 50, 20, 30, 40, and 50. And then I'm going to graph my data there. So I've got a dot at 17. I've got a dot at 32. I've got a dot at 22. A dot at 45. 30. 36. 51. 27. Where am I? 37. 47. 35. 33, 44, and then 22, which we had one of those already, so must be that, and a 31. Okay, so there's my dot plot. It's mostly single level. There's not a whole lot of like gaps anywhere. I wouldn't say that there's a large skew pulling in one direction, so the graph shows no skew or outliers. All right, so we're good with our conditions. So great. All right, so now let's talk about the formula that we use for significance test for mean. So our standard test statistic, if you remember, this is the same regardless of what you're looking at. It's the statistic minus the parameter divided by the standard deviation of the statistic. Okay, it says in an ideal world for test of the null hypothesis mean equaling the mean, our standardized test statistic would be a z. However, we will most likely not know the standard deviation. If we're testing the mean, it's not really possible for us to know the standard deviation. So that was the same thing, the same problem we had when we were doing confidence intervals of means. So because we don't know the samples or the population standard deviation, we're going to use the sample standard deviation. But the fact that we're using the sample standard deviation means that we have to use the standardized test statistic, or in other words, the standard error of X bar. So the denominator is going to look a little bit different than just dividing by the standard deviation. Okay, we're going to use S of X. And we're going to call this T. These are T procedures when you're doing mean, because we're going to factor in those degrees of freedom to find our test statistic, and that's what's going to allow us to have a little bit more wiggle room because we don't know the samples or the population standard deviation. Okay, so let's just go back to that conversation about T. We talked a little bit about T when we were looking at confidence intervals. It says when we perform inference about a population mean using a T distribution, the appropriate degrees of freedom are n minus 1. So a T distribution is described by a symmetric single-peaked bell-shaped density curve, so very similar to a normal curve, except any T distribution is completely specified by its degrees of freedom. So it factors in degrees of freedom because we don't know the true standard deviation, so we have to allow some more room in our curve. So it says when performing inference about a population mean based on a random sample of size n, when the population standard deviation is unknown, we use the T distribution with the degrees of freedom n minus 1. We can't use Z, we don't know the population standard deviation. We use T and we go off the sample size to get our degrees of freedom. So you can kind of see they talk a little bit about the different degrees of freedom. When you have 2 degrees of freedom, that's this red dotted line. Look at how much higher that red dotted line is above the blue line and the purple line. The purple is that standard normal curve, okay? So when I say that the degrees of freedom give us some more wiggle room, there's more area out in the tail. When I only have 2 degrees of freedom, meaning my sample size was only 3. If I had a sample size of 3, that means I have 2 degrees of freedom. I have a lot more room in the tail. And that just gives me it's kind of just like a safety net of we're not totally sure on this standard deviation. We're going on the sample standard deviation, but we're not totally sure that that's going to be the exact population standard deviation. So we need to allow more room in the tail. And the smaller the sample size you have, the more room you need to allow for, because we all know that increasing your sample size decreases your variability. So if you have a really small sample size, you have a lot of variability, which means you need to have a lot more room in that tail. Your tail probability goes up. When you jump up to 9 degrees of freedom, Now look at the blue line. The blue line is still above your normal curve, but it's definitely below the red line that only had 2 degrees of freedom. So there's still extra room in the tail probability, but there's not quite as much as if you only had 2 degrees of freedom. So that's just one point to kind of keep track of. It says as the degrees of freedom increase, the t distributions approach the standard normal curve. So you don't need to account for nearly as much area in your t distribution as you increase your sample size. Okay, so take that for what it's worth. All right, so if I carry out the significance test, now we have to find that t star value. So the t star value, it says we can use table B to find a p-value for the appropriate t distribution when performing a test about a population mean. In the Better Batteries example, you're looking at mean equaling 30, and the alternative is that the mu is greater than 30. So here's your formula for that. You had a sample mean. The sample mean from that table of the 15 batteries was 33.93. Subtract it by 30, because that's your mean, and then divide it by your sample standard deviation divided by the square root of the 15, okay? That gives you a t-value of 1.55, okay? So you've got a t-value of 1.55. You also know that your degrees of freedom are 15 minus 1, which is 14, okay? So your t-value is 1.55, and your degrees of freedom put you at 14. So here's where this gets a little tricky when you're using the table, okay? So if you're using the table, that 1.55, you have to find where it's located in the row of 14 degrees of freedom. So in the row of 14 degrees of freedom, the probability of 0.1 was 1.345. The probability of 0.05 is 1.761. So really all the table tells us is that our probability is going to be between those two somewhere. I know that it falls in here somewhere, but I'm not sure exactly where, okay? So if you're using the table, you get an approximation. You end up between two values, but you don't get an exact probability. Now, so here's where we have kind of some problems. Table B has limitations, okay? Table B has limitations for finding the p-values. It gives an interval of possible p-values for a significance test, but it doesn't give you the exact p-value, okay? It's limited based on what probabilities are listed already in the table. So all we're going to do is find a t-value and find what it's between. But that's not always super helpful. It's often more helpful for us to have that exact p-value to be able to make a decision based on whatever our alpha level is. Okay. The other problem is, using 14 degrees of freedom, our sample size was 15, so 14 would be my degrees of freedom. But what if your sample size is 48? If your sample size is 48, you need a degrees of freedom of 47, but you don't have 47, you have 40. So you have to go down all the way to 40, thus making your p-value more inaccurate. Okay, so using the table has limitations. Now, you've heard me talk about this before, but it's kind of an outdated practice to use this table. So your better bet is going to be putting this into your calculator. Okay, so now let's take a look at a different example, and we're going to talk about how to do this alternatively instead of using the table. It says, suppose you want to perform a test of mean, your null hypothesis mu being 5 versus an alternative hypothesis of mu not equaling 5. Okay, notice that this is a not equal to test. That means it's two-tailed or two-sided. At the significance level, the alpha level of 0.01. A random sample of size n equaling 37 from a population of interest yields x bar being 4.81 and your standard deviation being 0.365. Assume that the conditions for carrying out the test are met, so we don't have to do conditions here. Great. It says, explain why the sample result gives some evidence for the alternative hypothesis. So what we're looking at here is the fact that our sample mean is different than our population mean, or what we assume our population mean is. Okay, so x bar is equal to 4.81, which is different than 5. didn't mean to put my comma there, then 5, which gives us reason to test. Okay, so then it says calculate the standard test statistic for the p-value. So here's our standard test statistic. Here's what this is going to look like. You've got an equation of t equaling sample mean minus population mean divided by sample standard deviation over the square root of the sample size, which was 37. Type all that into your calculator. 4.81 minus 5 is going to be negative 0.19. The denominator, 0.365 divided by the square root of 37 gives me 0.060. And then negative 0.19 divided by my second answer, I get negative 3.17. Okay, so that's my t-value, negative 3.17. So here's where you could go to the table, okay? If you go to the table, table B would tell you, so table B, I'd use degrees of freedom of 30, because my degrees of freedom are technically 36, but 36 isn't in the table, so I'd have to use my degrees of freedom of 30. I'd look in that row for 3.17, and where does it fall, okay? Now, we've talked about how this is not going to be the most accurate way of doing this. I'm not going to use this method. I'm going to go to technology, and I am going to plug it into my calculator. So really what I want is, I want the probability that t is less than or equal to negative 3.17, and, or I should say or t is greater than or equal to 3.17. This is two-sided. So really, when I'm looking at my normal curve, I'm looking at down here and also up there. So I need both parts, okay? So I need to go to my calculator. If I go to stat and I go to calculate, I go to tests, I'm gonna do t-test. T-test is in your stat menu. So my mu, that you have to put in the null. So the null is going to be 5. The x bar is going to be 4.81. The s of x is 0.365, and your sample size is 37. Now on my calculator, I have an option to pick two-sided, the not equal to, the less than, or the greater than. I'm going to do two-sided here because that's what I want. If your calculator doesn't have that, then you need to get your probability and double it. So whatever your probability is going to be, then you have to double it to get the two sides. My calculator gave me that option. So when I type all that into my calculator, I end up with a p-value of 0.003. And you can keep going. The calculator does keep going there, but 0.003 is enough for us to make a decision. Now, let me write down for you what I typed in. So this is t-test, and I have mu equaling 5, x bar equaling 4.81, s of x equaling 0.365, and n equaling 37. Okay, so if you do not have that stat wizard, a lot of you have calculators that don't have the stat wizard that tell you what to enter in. This is the order that I put in my values. I put in the mu, then I put in the x bar, then I put in the standard deviation, then I put in the n, okay? When you do that, if you don't have the stat wizard, you might get a p-value of 0.000 or 0.0015, and you'd have to double it because this is a two-sided test. So this is the question here. Let's just make sure we actually answered the question. Calculate the standard test statistic and the p-value. So my standard test statistic was that, my p-value is that. And then I can use that to make a decision at the alpha 0.01 level. I would then go through, if I'm looking at 0.01, 0.003 is below, and I would reject the null. So I could use that to make my choice afterwards. So there's a couple of things that are wrong in your notes right here. This computer or this calculator output is the wrong values. They have it, for whatever reason, they just screenshotted the wrong values. So I'm sorry about that. The test statistics are correct, but the calculator outputs were wrong. So what it looks like is you have TCDF, because it's a t-test, so TCDF, and then you have all of those things. This is your probability, so you need your negative infinity to your test statistic, negative 3.17, and then your n, which is 36. Okay, and the reason you're putting your n in is because of the t-value. So those are the values that give you one side. This just gives you the left tail. If I was going to draw a curve right here, this is negative infinity up to negative 3.7. So that gives you the left tail. But if you are looking at a two-sided test like we were, so then I want to come over here, I need to take this and I need to multiply the whole thing by 2. And that's going to be my p-value. So same thing, same test, you do the negative infinity up to the negative z or t score, and then your n value, and then when you multiply it by 2, that gives you the right tail up here, and the whole p-value for a mu not equal to 5 alternative. All right, that's going to be the end of our first part of section 11.1. So hang tight. We've got a couple more parts to get through, but hopefully that at least gives you a brief introduction to doing a significance test for means. Thanks for tuning in.